Just to introduce myself again, my name is Rob Tice, Technical Account Manager here at AdaCore. Before we start, fun fact about AdaCore, this is our 25th anniversary, which makes it much cheaper for us to rent cars now. Okay, so this morning we heard a lot about security, and we got very technical, very specific. So to keep the trend going, we're going to zoom way out and talk about the market. One of the reasons why we like to have these types of events and why we like to talk to you as much as possible is because you let us know what your challenges are, what your challenges are going to be. And that kind of informs this actual presentation. This is sort of identifying what trends we see in the market, both short-term and long-term. And the next presentation we have is by Arnaud, who's our Director of Engineering. He's going to be presenting the product roadmap, which is really the response to this. So based on your feedback through tickets, through visits, through events like this, we get this information, and then we're able to use that to provide you solutions. So again, we'll talk a little bit about what we see, and then in the next presentation, we'll talk about what we're doing about it. How many people in the room are currently using PowerPC processors? Okay, very few. That's a good thing, because now let me explain a little bit here. 2005, Apple dropped the PowerPC and went to Intel. That was sort of the first big note about PowerPC going, maybe there's a problem here. One of the big problems with PowerPC is just the way that they did their business model. It's an old school engineering company. It's very difficult to get proprietary rights to distribute PowerPC chips. They're very expensive. So we're seeing people move away from PowerPC to other things. Sort of the writing on the wall for us is specifically that in GCC 8, the GCC community deprecated the E500 architecture, which is an old PowerPC architecture. You know, there's no plan for them to deprecate anything about their normal PowerPC instruction set or the PowerPC 64 stuff. But we're starting to see them start to go look and go, who's using this stuff? In GCC 9, they've actually removed all that code for the E500 architecture. It's actually the PowerPC SPE instruction set. Another compiler backend, LLVM, which we'll talk more about in a minute, is a competing sort of compiler backend that's sponsored mostly by Apple. They barely even have any support for PowerPC at all, because they don't see that as there's any future there. So you might be thinking, well, I'm on a PowerPC now. Where are people going? They're going to these types of things, where we have ARM, Intel's, and this other thing, RISC-V, which we heard about a little bit this morning. Why are they going to these things? Well, you'll notice that these are fairly modern sounding names. You've heard a lot of these in tech companies, especially in Silicon Valley, doing a lot of work with these processors. You don't hear much about people doing stuff with PowerPC anymore. So those people who are on PowerPC, you know, we support. We're gonna continue our support for PowerPC for as long as we possibly can. But as you start to identify that it's difficult to get chips, that's the biggest one, right? If you need to get a new board and no one has PowerPC chips anymore, are you going to keep buying them off of eBay? So what happens if you have this old PowerPC compiler? What are you going to do? Now, we want you to know that AdaCore can help you out with this. And we want you to come to us early on in the process, because again, part of this presentation is to show you what information we've collected from you, and then the next presentation is to show you what we're going to do with that information. As you're going through your tech reviews, as you're saying, okay, in the next 5 years we need to change off of this processor because we can't get it anymore, and you start to do research into this sort of thing, contact us early. Say, hey, look, this is what we're trying to do. Here's where we need to go. What can AdaCore do to help us get there? The earlier we're involved in that process, the earlier we can let you know exactly what our solutions are and what they're going to be, so that you can make decisions to minimize the impact on your systems. Now, one of the big things switching from PowerPC to any of the other processors I just listed, the endianness problem. we have a very nice article online that we used to have this thing called Ada Gems, which is kind of like these cool things in the Ada language. And one of them was about this scalar storage order pragma, which allows you to actually specify the record layout of an object, and then the compiler inserts instructions to actually do the flipping for you if you're specifying a endogenous format that's different than the system format. This is particularly useful, especially if you're coming from a PowerPC system and you have network interfaces where you had a big endian network interface and a big endian processor. You didn't have to do anything. Now you switch to a little endian processor, but you still have big endian network interfaces. We have to manually flip all the records, right? Well, luckily with this, the compiler can do that for you. Very important, this does introduce instructions that are generated. So you do take a runtime hit here, but for instances where you do need to do this conversion, this makes it so that you don't accidentally have problems by, let's say, hand coding incorrect layouts. So if people are moving away from PowerPC, we mentioned that they're going to ARM, Intel, RISC-V. What specifically are they going to? For those using ARM right now, you'll notice that there's two real levels of processors that they have. So the Cortex-M, the Cortex-R are kind of their microprocessor architectures. The Cortex-R is really their safety processor. They have things like dual lockstep processors and things like that. These are their small systems. The Cortex-A's are their application processors. This is where you'd run things like VxWorks or Linux and things like that. Some people are going to Intel. Intel has its host of problems, as you might have seen in the news with all of their problems with their instruction sets and things like that. Intel's also happen to be particularly energy hungry. So if you're in a low power system, sometimes it's difficult to use Intel's. But they do have a lot of processing power. So if you're coming from a large PowerPC, you can get a Intel Xeon and get infinitely better processing out of that. And you have a future in the silicon also. And there's this other thing, RISC-V. And I'll kind of get into what this is in just a minute. But these are our typical homogeneous architectures. This is where you have just a processor that does processor things. But what a lot of people have been moving to are these heterogeneous type processors, and some of you in this room are probably already using this one. It's a Xilinx UltraScale Plus SoC. This is an FPGA with a 2 or 4 ARM A53s, I believe, or A72s attached to it. The reason this is interesting is you can use the FPGA for your typical FPGA work, like, for instance, matrix inversions, or doing large parallel video processing, or doing large parallel data processing, or if you have custom interfaces. And then you can use your processor for your typical processor things. And these are on the same silicon. So now you don't have to worry about laying out multiple chips on the same board and worrying about high-speed data interfaces in between. If anyone here has done hardware layout, you'll kind of know what I mean when high-speed data layouts are quite costly. So this is particularly interesting. There's also competitors to this Xilinx. I know the Xilinx one is sort of an industry favorite because it's a well-known brand. But there's this other company, Microsemi, owned by Microchip. You might also know them as Atmel. They have a PolarFire, which actually is the same thing, FPGA, with a RISC-V attached to it. So those are really your FPGA-based heterogeneous architectures. There's one here at the bottom, which is kind of interesting. Has anyone gotten a chance to play with any of the NVIDIA Jetson boards? All right, a couple hands here. They're quite cool. There's ARM processors attached to a GPU, so it's general purpose. And if you want to play with things like TensorFlow or do any sort of machine learning, that's a really great platform just to play around. If anyone's a nerd like me, this is what you do at night and on weekends. So you have all these abilities to use your typical processor layouts or heterogeneous layouts. The interesting thing from the AdaCore perspective is we support all of this stuff. In the homogeneous sense, this makes sense. These are things you're used to. In the heterogeneous sense, we support the processor side. So if you do have the Xilinx UltraScale and you're using ARMs on there, we can support those ARMs, whether it be Linux or bare metal, or even VxWorks or things like that. If you're using the NVIDIA, same thing. We support those ARMs. So let's get back to risk 5. Who and why? We've already sort of heard a presentation this morning about one company you may have heard of using risk 5. Another big adopter so far is Western Digital. They're actually one of the main members on the risk 5 committee. You'll notice that both of these manufacturers are silicon manufacturers. So they're actually creating their own silicon. Risk 5, the reason Risk 5 is interesting is it's kind of the first open source processor IP out there. Let's look at ARM, for instance. If I'm Apple or one of these companies and I want to create my own processor and I want to put an ARM processor on there, I have to lease or I have to have some license with ARM, and I have to pay royalties, I have to pay design fees, I have to pay all this money in order to get this ARM IP onto my silicon. With Risk 5, it's open source. So now I have the ability to design my own processors and design my own chips, and I don't have to pay as much money in terms of royalties and fees. What's interesting about this is that the industry is kind of always has this cyclical relationship with open source. AdaCore has been open source from the beginning. We like open source. So when we see hardware manufacturers who now have the ability to use open source hardware with our open source tools, that makes us happy. You'll also notice that these two companies here are not your typical Ada companies. Western Digital, I don't believe is using Ada yet, but NVIDIA definitely is. And they're not your typical company, meaning they're not aerospace or defense. But we heard this morning why they're using Ada. So we have to ask the question, if a new industry is coming to us and they're asking us to use Ada, why are they doing it? Well, let's look at the usage of Ada over the years. What's the traditional market? The traditional market is aerospace and defense, right? One of the interesting things about aerospace and defense is that they've been developing fairly decent code. You know, I don't know if you guys have other opinions about that. For a fairly decent amount of cost, for a fairly decent cost. So they haven't had significant cost overruns. There hasn't been significant safety or security problems so far. So when other industries are now coming to an area where software is very critical to the system, they're going, what other industries have this exact same problem? They're looking at aerospace defense, railway, and our traditional customers. They're saying, well, these industries have done it right so far. What are they doing? So let's take an example. This is a graph from a study that was done by an independent research company. This is actually a graph. This chart was actually taken from the case study, which you can actually find a paper copy of in the back of the room there. A company called VDC Research did a study where they looked at the cost of using Ada in a typical aerospace and defense environment versus actually using C versus other languages. So as you can see here, C is the baseline. C++ gives them a little bit of cost benefit. Java gives them a little bit. I'm not sure if I've ever seen C# used in aerospace and defense, but okay. And then Ada. What's interesting here is that there's a significant cost savings here. And to be fair, we paid for this study, so you can say, oh, well, maybe it's biased, but we did not conduct the study. So this all comes from the industry. So these new markets are now coming and looking at this and going, well, we're spending a ton of money on test. Because in order to be safety critical or security critical, they need to run very significant amounts of test suites, and they need to be very rigorous in terms of how they do that. If they use Ada, a lot of these tests that they need to do tend to pass the first time. So they're finding that there's a lot more savings later on in the development process. There's another benefit, though. There is the cost benefit, but let's look at some of these markets that maybe are coming to us now. Let's look at the automotive market 10 years ago. Most of a car in a fairly recent past was still very much mechanical. most of a car now is very much not mechanical. So in the very recent past, the automotive industry has started introducing software in critical pathways in the car. So traditionally, software was used for the radio, maybe the thing that moves the seat back and forth. Now it's used for steering, it's used for braking, it's used for gas, it's used for detection of what's around you, it's used for braking, it's used for parking, it's used for driving. So, of course, we see here this is a self-driving example. This is a very marketing photo. I apologize for that. But what this is identifying is that there's tons and tons of systems now running inside of a car. Now, if they develop these systems without any safety or security protocol, that's what happens. This is a Tesla. If anyone is familiar with what's been happening with Teslas recently, in autopilot mode, they have a tendency to crash into stationary objects. Why is that? Because their sensors that detect what's around them uses a noise filtering technique that filters out stationary objects. Think about when you're driving and you have poles on the side of the road. As the car is driving, it's going to have their vision systems and their LiDAR systems see all of these stationary poles, and they're going to say, object, 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 swerve, 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 and you're going to be all over the place. So in order to fix this, they've put in these noise filters that said, any of these stationary objects we're just going to ignore. What happens when there's an emergency vehicle parked on the side of the road? Or the lane is closed because there's a police car there. Unfortunately, that filtering mechanism doesn't quite work so well. So you have all of these systems that are now life critical that weren't a long time in the recent past. So these industries, and I'm identifying specifically automotive and let's say healthcare in this example, are going, okay, now we have software that means something. How are we going to make sure that this software is safe for people to use? One of the ways we regulate these things is through certifications. Those of you in the aerospace and defense market and or railway might be familiar with these on the right. These are our traditional standards. This one, DO-178, being the avionics standard, is probably considered one of the most stringent software standards out there. And really, the idea is that by regulating the process of software development and creating checklists of actions, you should be able to generate safe software. Up until recently, the automotive industry and the healthcare industries, they've had regulations and certifications, but they weren't typically followed, and or there wasn't a lot of action to make sure that people actually were held accountable for them. But now these industries have all this software, which means something to the safety of the people using these things. So now there's a lot more interest in these certifications. AdaCore is really good at these. We do these every day. In fact, our CEO, or actually our president, works with the FAA for the DO-178 certification. We have experts in the railway certification. We have experts in the space certifications. And we're now becoming experts in the automotive certification. When we have customers in the healthcare one, we're going to be experts in those. Because as people who deliver you software, we want to be able to that we deliver you software that you can use in these contexts so that you can develop the software you need to do and trust that our actions on our side can help you develop your software. Our stuff's all taken care of under these standards so that you just focus on what you have to do. I kind of like this one. A lot of us, when we say it, will just keep adding 6s and 2s at the end. So ISO 2626, 2626, is that enough yet? So as we're going through certification, one of the big questions that people ask is, what software are we actually going to put on the target? Are we going to use an RTOS, or are we going to just write it on the bare metal? So a lot of people will come to us when they're doing their trade studies. And they'll say, hey, look, this is what we need to do. This is where we are now. This is where we need to be in 1, 2, 5 years. What are our options? And a lot of times they are asking us this question. Traditionally, people are coming from these types of RTOSes. A lot of VxWorks, a lot of LinksOS. Pike OS we see a lot less in the US, but we see that very heavily in Europe. But there's a new one on here that we've been hearing about a lot more recently that hasn't come up in the past. Real-time Linux. Now, the interesting thing about real-time Linux, it's open source. So this goes back to what I was saying before. We're seeing a lot of move from these closed source systems to open source systems, specifically because it's cost savings for you and you have transparency into what's going on. The interesting thing about AdaCore is that we know that this is what you are looking at, so we support all of these things already in many of the architectures that I mentioned earlier. So again, if you're looking at picking an RTOS, come talk to us and say, hey, this is what we're thinking about doing. Do you have support for this? What will our porting challenges be? How can you help us get through this? And we'd be happy to help you out there. But there is an alternative to RTOSes that has been becoming a little bit more popular more recently, and that's just going right on the bare metal. Traditionally, there's been a significant technological barrier of entry to this, because writing on the metal is intimidating. There's a lot of stuff to handle. However, AdaCore does provide a lot of runtimes which can help you do this in a way that makes it so that you don't have to do a lot of work at the low level. For instance, if let's say you have your UltraScale Plus board and you want to run tasking on that, we have runtimes where you can utilize all the cores and do your multi-core tasking just like you would on an RTOS with a lot less code running on there. Let's say you want to go through certification and you want to certify less code. Remember, more lines of code means more cost. So if you were to get a certified version of an RTOS, it's very expensive. However, if you were to get a certified version of just a runtime without that RTOS, you're going to save tons of lines of code, meaning a lot of cost. You can utilize one of our small footprint or zero footprint runtimes. This gives you the ability to run Ada in the zero footprint mode in a single task. In the small footprint mode, you have tasking. We decrease the amount of libraries that you have access to, specifically because that's more lines of code for you. So the less lines of code for you, the cheaper it is for you. So we have these abilities for this all to be custom for you. So again, as you go through this, you go, hey, we're thinking about bare metal. We're currently on VxWorks. We're using these types of libraries. What type of profile would we need if we were to do bare metal? Come talk to us. Another interesting trend we're seeing recently are hypervisors. These are two companies that currently have hypervisors in the market. Wind River, you might be familiar with VxWorks. They have a Helix platform, which allows you to do virtualization. And then Lynx has a similar technology. Let's look at Wind River first. This is a chart right off their website. The whole idea here is that when you have a hypervisor, you have the ability to run multiple operating systems. Think about this as like your laptop and you're running virtual machines. The whole idea here is that we can make these virtualized operating systems be time and memory partitioned. So you can run this in, let's say, an ARINC setup for a D0178. Let's think about your application. I mentioned earlier you might have an application with, let's say, network interfaces, but then those network interfaces aren't doing anything critical. All the critical stuff is happening in algorithm land, and that needs to be, let's say, certified, but let's say your network interfaces don't. Do you really want to write all of the network stacks in bare metal? You kind of maybe want to get that from an RTOS, but you maybe want to run your algorithm code in bare metal so that you don't have a lot of layers in between you and the hardware. With this type of setup, you have the ability to pick and choose what you want to do. You can have, let's say, VxWorks running in one core or one partition. You can have another VxWorks running in another partition if you want. And you can have other OSs like Linux, or you can even be running bare metal in here. This allows you to have multiple operating systems running in the same platform. This makes it so that you can select what you do and where. So you get the benefits of the the benefits of the OS or lack of OS where you need it, and not the cons of that in other places where you don't need it. Similar setup for Lynx OS. Theirs is called Mosaic. We're noticing that all of these names have super marketing-y, snazzy titles now, Helix and Mosaic. I think we're getting into Apple marketing land here. But this is a very similar setup. It's a much more complex picture, but effectively you have the Lynx secure partitioning system, which is effectively like the hypervisor, and then you have the RTOSs or bare metal running on top of that. And then in this picture is just the ability to communicate between those platforms so that you can keep everything partitioned. So again, with this type of system, you have the ability to pick and choose what you want and where. So far we've really only talked about safety. We talked a lot about security this morning, but we talked a lot about specifics of security this morning. Let's zoom out a little bit. I was at a customer a while back, and they said that when they got a new contract from their customer told them that they must solve cyber. And they went, I have no idea what that means. So they came to us and said, what does solve cyber mean? And I went, okay. Well, that really depends on what your customer is looking for. In many cases, your customer is just looking for software quality, which also means software security. In other cases, they're looking for software to be impenetrable. In other cases, they're looking for the IT department who maintains the development systems to make sure that their systems are secure. There's tons and tons of definitions of this. Our best interpretation of this, at least in terms of you developing applications, is found in this book. I know a lot of you have already seen this. It's in the back of the room. Please take one on your way out. This is also available as a PDF on our website. This is what we have available today for you guys to do. This goes through CodePeer, goes through Spark. It goes through what's available in the Ada runtime. It also goes through what you can do to mitigate certain types of application security. One of the interesting things about CodePeer and Spark is that it helps you with software quality, which helps you with language level security. So most exploits at language level security are things like doing a buffer overflow to access information you're not supposed to, or forcing an integer overflow to mess up execution of a program, or messing with the stack pointer so you can jump to parts of the program you're not supposed to be. These are all things that are kind of like at the language or the processor level. But a lot of times what you're being asked in terms of cybersecurity is actually at the application level. Like for instance, if you have a SQL database in your system, I'm not sure why you would, but let's say you do. And you would need to, let's say, make sure that someone can't insert a input string that says drop all tables. There are ways at the language level to make it so that you can do language level checks to make sure that people can't do that, even though that's an application level item. This book goes into sort of some of these applications and how you can use the benefits of Ada and Spark to kind of help figure this stuff out. What's more interesting, though, is what can you do tomorrow? The static analysis, you might recognize this slide. I did steal this directly from Quentin's slide, this presentation this morning. We already have this. This is already, you already have access to some of this. These two are kind of the interesting ones, and Abe did a presentation this morning about fuzzing. So we're seeing fuzzing pop up in a lot of the tech market, usually in terms of web applications. Because that's typically where you're going to have tons of inputs that can potentially be malicious. But think about an application where you have inputs that could be malicious, but they're coming from a sensor. And you want to make sure if that sensor malfunctions, you gracefully can handle that problem. This is where fuzzing can help you. If you have an instance where your hardware is accessible, meaning someone has physical access to the hardware, this is where you're going to want some of these compiler hardening techniques. So these are the things we're currently working on to make sure that you have access to these things as you start to get these mandates from your customer. Just making sure I'm not running out of time here. So as we start to introduce a lot of these new tools, you might be asking, well, we have a workflow, and we have tools in our workflow. How are we going to fit all these new tools in our workflow? I always find when we have this discussion, the word integrated gets used way too many times. But what they're really asking is, we have this, where do you fit in it? You might recognize a lot of these tools, and you might be using a lot of these today. A lot of version control systems, requirements management systems, build systems, test systems, all of these things. So when we get asked the question, how does AdaCore integrate in with blank being one of these, or the hundreds of other tools which are not listed here? Our answer is, well, that's a lot of tools to integrate in with. However, we're going to try to help you in 3 ways. Number 1, we're going to try to be as flexible as possible. Someone asked me once why all our tools are command line first and not just integrated into the IDE like a lot of other vendors. My answer to that was, let's say you have a CI system, generic, whatever it is. You need to call this tool from the CI system. Do you really want to call into an API that provides all of the I/O for our tool and customize the APIs and figure out exactly how everything works? Or do you just want to automate a bash script? That seems much easier, right? If you're doing bash automation, that's as flexible as you can get. We also have the ability to extend things. One of the benefits of Gnat Studio, I should start calling it the tool formerly known as GPS. Prince reference there. One of the benefits of Gnat Studio is that under the hood there is a Python interpreter which does allow you to write your own Python plugins. So let's say you have a workflow that you currently want to automate but you want to use Gnat Studio. You can have Gnat Studio trigger your other applications via custom buttons or custom menus or custom integration workflows. And most importantly, as you're going through this, talk to us through the support mechanism. Because you might ask, hey, we need to integrate these tools, they work like this, how can we do it? And that's when you come to our engineers and we say, okay, these tools work like this is the best way to integrate this tool into this type of tool which will work like this. We get a lot of questions about integrating into things like Jenkins or Bamboo or how to integrate in with version control systems. So we get those questions a lot. So we've become very good at understanding how our tools fit into this ecosystem. A lot of our customers also do suffer in silence a lot here. And we do ask that, come to us as early as possible, even if you think the answer or the question is trivial. Because despite the fact that you might think it's trivial, it might be more complicated than that. And even if it is trivial, we're still happy to help you out. The more information you give us, the better this presentation gets, the better our roadmap gets. So you guys inform us about how we're going to be technologically. Before I mention a tool called LLVM, they have a really cool logo, something out of like Game of Thrones or something here. LLVM is a compiler backend that's really been driven by Apple. And it's sort of a competing technology to the traditional GCC. From the start, AdaCore's tools have been based on GCC. In fact, actually, in our company, we have a lot of engineers who very regularly contribute to the GCC community. So we're very familiar with GCC. This new LLVM stuff has been picked up by a lot of big tech companies, specifically because of some of the benefits. So let's actually look at sort of the comparison here. If we kind of consider LLVM to have a similar functionality, meaning the Ada front end or the C front end or whatever generates a tree, that tree then LLVM or GCC takes that tree and then generates object code. So if we were to consider those two similar functionalities, some of the benefits of GCC. GCC supports traditional languages. Now I'm putting Ada in here as a traditional language. We all know that it's a little bit more advanced than I'm making it look here, but GCC has had native support for Ada for a long time. It also supports things like Fortran. Does anyone still use Fortran here? Oh, I got one. And things like Go, which is actually kind of a much newer language. They're supporting things like PowerPC, as I mentioned earlier. There's a lot more language extensions, a lot more better support for assembly language features, and currently the Linux kernel can only be compiled with a GCC compiler. LLVM has different benefits. One of the big benefits is that it was designed as a modular framework. GCC is a very big monolithic beast. So dealing with it can be kind of difficult, and getting involved with it, there's a pretty big barrier of entry. Whereas with LLVM, since it is modular, it's much easier to use functional pieces of it in a much more controlled format. It's more of an API than it is a big monolithic tool. GCC is notorious for messing with the C and C++ standards. Like there's a GCC version of C and GCC version of C++. Whereas LLVM has tried to conform a bit more strictly to the standards. You can decide whether that's a good thing or a bad thing. And one of the reasons, because it's modular, it has all these tools built in. Like you have the ability to do static analysis or linters or syntax checking, syntax highlighting, completely agnostic to actually what the language is. So this all kind of gets pretty neat in terms of what you can and can't do with it. And that's one of the reasons why technologically some people think it's superior to GCC. So Arno will present in the next presentation here exactly what we're doing with LLVM. But if we are starting to experiment with this, and it is something that we are working with so that we can support future things. Like for instance, VxWorks 7 is based on LLVM compilers, so that's something that we want to be able to support in the future. Arno will go into more details about that in his presentation. So I only have a few minutes, and I do want to talk about C++. C++ wasn't a standard until 1998. The C++ standard was huge, it was ugly, and it didn't have a lot of the features that we think of C++ today. Most applications that I've seen in this industry that are using C++ are using C++ 98, which is effectively object-oriented C. The cool stuff in C++ came in C++ 2011. The whole idea from C++ 2011 on was to go fast, break often. Now, there's an interesting trade-off here. By going fast, breaking often, we have the ability to introduce tons of new features. Like for instance, in C++ 11, C++ 14, which is actually more of a bug fix release because they broke so much in C++ 11, but it's okay. C++ 17, C++ 20. Now, tons and tons of features have been put in the last 9 years. However, most of those features are getting fixed with every revision because they were done poorly the first time. So you have a mentality in C++, which is go fast, break often, but you have the ability to use a lot of new features. So we're seeing a lot of uptake of C++ in the industry, and one of the reasons is because of all these new features. This is a different mentality than we have with Ada, where we try to keep as stable as possible because we're considered a safety language. So tomorrow we have a presentation where we'll cover what we have with C and C++ and how we're handling that as a company. You might be asking, what about Ada standards? Arno will cover this more in the next presentation. If you do want to learn more about Ada standards and you want to talk to us or talk with the community about what's going to happen in Ada 2020 or what's going to happen in the next versions of Spark, we have an open format where you can go and actually do RFCs to actually contribute to the Ada language.